You've probably seen AI do something that looks like straight up magic, right? Like taking a regular photo and boom, it's a painting by a master. Or changing summer to winter in a picture with just a click. Well, today we're going to pull back the curtain on the brilliant paper that unlocked one of these magical abilities, image-to-image translation. And this is the image that made this whole thing famous. On the left, you've got a horse. On the right, that same exact horse, but now it's a zebra. And here's the crazy part. The AI figured this out without ever seeing a single picture of a horse next to its zebra version. It just saw a folder full of horse photos and a totally separate folder full of zebra photos. And that right there is the million-dollar question. If you don't have perfectly matched before and after examples, how on earth can a machine learn the rules? How does it know to only change the stripes and not, mess with the shape of the head or the grass in the background? That's the puzzle we're about to solve. To really get why this paper was such a massive deal, we first have to rewind a bit and look at what AI research was like back then. The entire field was stuck on one very big, very limiting idea. See, back then, everything needed what's called paired data. So if you wanted to teach an AI to colorize an old photo, you had to show it millions of examples of the exact same image, one in black and white and one in color. The new problem this paper tackled is unpaired training. You just have a big pile of A's, let's say horses, and a totally separate pile of B's, zebras, with zero direct links between them. And this was a huge bottleneck for researchers. I mean, getting that paired data is incredibly hard, sometimes impossible. Just think about it. How would you find a photograph and a Monet painting of the exact same landscape captured at the exact same second? Or find a picture of a random building and its perfectly matching architectural blueprint? For tons of creative ideas, you just can't get that kind of data. And this is where things get really, really clever. The researchers brought in an idea that was so elegant and so powerful that it just changed the whole game. And it came from a place you might not expect. First, super quick primer. This whole thing is built on something called GANs. The easiest way to think about it is like a team of two AIs. You've got an artist, the generator, who's trying to paint a perfect fake zebra. And then you have an art critic, the discriminator, whose only job is to look at that painting and shout fake or real. They're in this constant competition, and by fighting each other, they both get ridiculously good. Now, the core idea here is actually super intuitive. Forget pictures for a second. Think about Google Translate. If you translate hello into French, you get bonjour. Now, what happens if you immediately translate bonjour back to English? You should get hello, right? If you get something else, like greetings, you know the translation isn't perfect. It's not fully reversible. And that simple little test is the key. And that's the big breakthrough. It's formally called cycle consistency. It's this simple but really profound idea that any good translation has to be a two-way street. If you go from A to B, you should be able to get right back to A without losing the important stuff. So here's how they applied that to the images. The AI takes a horse picture, generates a fake zebra, and then, and this is the kicker, it uses a second AI to try and turn that fake zebra back into the original horse. Then it looks at its final horse and compares it to the one it started with. It does this millions and millions of times, and it does it in both directions, horse to zebra and zebra to horse. This cycle forces the AI to learn what zebraness really is, the stripes, while preserving everything else. And the results of this one simple idea? They were absolutely mind-blowing. It really laid the foundation for a lot of the creative tools we take for granted today. So for example, they gave the model a bunch of photos of Yosemite in the summer and a separate pile of photos of Yosemite in the winter. And using that cycle consistency trick, it actually learned to translate between seasons, adding snow, changing the lighting, all of it. This is a foundational concept for modern photo editing. And here you can see that two-way street in action. It could also take a winter photo and just imagine what summer would look like. It melts the snow, makes the trees green again, all without ever seeing a side-by-side example. This is probably one of the most famous applications, artistic style transfer. The AI looked at a bunch of Monet paintings, learned the rules of his style, and could then just paint any photograph in that style. This is basically the granddaddy of all those art filters you see in apps today. What's even wilder is that it could go in reverse. It could look at a Monet and try to generate what a real photograph of that scene might have looked like. It shows the model isn't just mindlessly copying a style. It's actually trying to understand and reverse engineer it. Okay, so how well did this thing actually work compared to what else was out there at the time, and what kind of ripple effect has it had on the field since it was published? Well, the paper had this real versus fake test, where they asked people to tell the difference between a real photo and an AI-generated one. And just look at these numbers. The other methods, they fooled less than 1% of people. CycleGAN fooled over 26%. That's not just a little better, that is a gigantic leap forward in realism. But hey, no model is perfect, and the authors were really upfront about that. It has trouble with big geometric changes, like trying to turn a cat into a dog. The shapes are just too different. And because it's only ever seen horses by themselves and zebras by themselves, it totally fails if you show it something new like a person riding a horse. It doesn't understand horse like we do, it just understands the texture. But even with those limits, the core idea of cycle consistency was a revolution. It blew the doors open for creating synthetic data to train other AIs, for improving simulations for things like self-driving cars, and honestly, its DNA is in so many of the powerful generative AI models that we're all talking about today. And that really gets to the heart of it all. The magic here isn't just about making cool pictures. It was about a fundamental shift, a new way to teach machines how to find connections between concepts without us having to spell everything out for them. It taught them to see the world a little bit more like we do. This is for entertainment purposes only.